lesson, we continue to learn ratio, conversion, and rates. So this is the second part of conversion and rates. So first of all, conversions. So this is something that we convert or converting between different units of measurements. So for example, so this conversion can be the conversion between different units of length, different units of time, different units of volume. So basically, any different units can be converted between each other based on a certain conversion rate or based on a given conversion rate. So for example, there are 20 inches in a foot, and there are 3 feet in a yard. So how do I compute the number of inches in a yard? Right, this is really just a multi ratios that we learned in the previous class, right? Because each conversion can be written as a ratio, and here we have 2 conversions, inches to feet, feet to yard, and eventually we want to know what is the conversion between inches and yard. Right, so first of all, we know the ratio 12 inches in 1 foot and 3 feet in 1 yard. Right? Then inches to feet 12 versus 1 is equivalent to, if I multiply by 3, is equivalent to 36 versus 3. And the reason I want to get the number 3 over here is that it is equal to the relative quantity in the second ratio, feet versus yard. Then this will help me to write inches versus feet versus yard to be a multi-ratio, which is 36 versus 3 and 3 versus 1. So that the inches, or the standalone ratio just between inches and yard, is 36 versus 1. Right, so this is one way by using the ratios, or by using the multi-ratio. The multi-way ratio is what we learned in the previous class. Now, using conversion factor, let's see how can we do this. So first of all, we know the conversion between inches and feet. We know 12 inches is 1 feet, and we know 3 feet is 1 yard. Here, when you do the conversion, not only in this example, but in the whole class, or anywhere that you want to do the conversion, very, very important is that keep the units. Keep the units in your calculation. So by the end, units will help you to examine that whether your outcome makes sense or not, or whether your outcome is correct or not correct. Right? If the unit doesn't make sense, if the unit is wrong, that indicates that something's wrong during your calculation. Or in the other way around, if your output is correct, then your unit should be also correctly representing the physical meaning of the question. Now, here I want to convert inch to yard. So if I'm multiplying the two fractions, 12 inches over 1 feet times 3 feet over 1 yard, I can do the number multiplication on one side and unit multiplication on the other side. So if I'm just writing the numbers together, first I got 12 times 3 over 1 times 1, and then I can keep writing the units, and in fact this feet on the both sides of the fraction can be cancelled out, so what left is inches over yard. And then it's really just 36 over 1, or 36 inches over 1 yard. And this conversion rate is the same as what we derived by using ratios. So for example, this is the conversion rate, right? So solving an actual question, for example, 6 yard is how many inches? Right? Again, keep the units during the calculation to help you verify if you get the correct result. So 6 yards, if I'm multiplying the conversion rates here, 36 inches over 1 yard is the conversion. Then numbers gives you 6 times 36 over 1, and the units cancel out the yards first, have inches left, and eventually that is 216 inches. So 6 yards equals 216 inches. Or the other way around, if I have 90 inches, I want to know how much yards it is. So 90 inches. This time I need to use my conversion factor other way around. It's also equivalent to 1 yard over 36 inches. Now you can see why I'm not using this ratio, because this time I need to cancel out inches. So that's why it's important to keep your units in the calculation so that you know that this is the right way to do the calculation, or this is the right way to multiply your conversion factor, right? Because the other way around, you won't be able to cancel out the inches unit. So here you can cancel out the inches unit, and you only have 1 yard unit left. And that's exactly what we want. We want to know how many yards. So it's 90 over 36 yards. And of course, if you want to simplify, that is 2.5 yards. Okay. So let's see another example. Density of water is 8.3 pounds per gallon. So this is 1 unit for density. And there are 4 parts in 1 gallon. Then how much does 7 quarts of water weight. So there's two ways to solve it. Let's try the first way is to convert to first of all write out the conversion, which is the density. Density converts weight over volume in terms of gallon or quarts, right? The question is asking how much is the weight given 7 quarts of the water. So density is conversion, that is 8.3 pounds. Pounds is the unit of weight per gallon, right, over 1 gallon. Gallon is the unit of the water, volume of water. And we know that 1 gallon is 4 quarts. So this ratio can be further, maybe let me write this way. 1 gallon is 4 quarts, right? So then gallon will be cancelled out. The new ratio is 8.3 pounds over 4 quarts. So this is also equivalent to your original density. Or in other words, it's just simply replace 1 gallon by 4 quarts. Now what I'm asked is, given 7 quarts of the water, 7, what is the weight, right? So 7 quarts of the water multiplying the density of 8.3 pounds over 4 quarts will give you the quarts canceled out. The only unit left out is pounds, which is the unit of weight. So I'm multiplying the right conversion in the right way. Eventually I'll get weight. And then the numbers will give you 7 times 8.3 over 4 pounds. And you can do the math, but eventually that is 14.525 pounds. So 7 quarts of the water weighs 14.525 pounds. So this is the unit conversion. Maybe let's see one more example, because sometimes you not only need to convert your unit, but also need to transfer your original unit, for example, from length to area. For example, if an inch is 2.5 centimeter, how many square centimeters are in a square inch? So first of all, area of square, if you know, is 1 square inch times to 1 square inch square, right? So that's the area. So inch is the unit of length, and inch square is the unit of area. So 1 inch, this is given that 1 inch is 2.5 centimeter, or 2.5 centimeter is 1 inch, right? This is the given conversion. So then 1 square inch is how many square centimeters? Let's see. 1 square inch. This time, if I'm only multiplying this conversion, inch and inch square won't be completely cancelled out. So which means I need to multiply it twice. or multiply the square of this conversion. So this equivalent to have 1 inch square times 2.5 square centimeter square over 1 square inch square, right? That's by the property of the exponent. And then inch square canceled out, right? Again, that is the importance of why you need to keep the units when you do the conversions. This tells me that I'm doing the right thing. I'm canceling out the inch squares, and the one just one, right? So that's 2.5 square centimeter square, and you can calculate the 2.5 square is 6.25 square centimeter. So that's the results. That's the amount of the square centimeter that can be represented in 1 square inch. Okay, so now after we see the examples of the conversions, we go to the last important concept, which is the speed as a typical case of the rates. Right, so speed is a measure of how fast something is moving. So then speed is a ratio of distance to time, right? So how fast something's moving along the time, and how fast is measured by the change of distance. So speed in mathematical expression, speed is distance over time. For example, the train travels 1 mile in 1 minute and 30 seconds. At this rate, or at this same speed, how many miles will the train travels in 1 hour? Right, so first of all, we know that the train travels 1 mile in this amount of time. So based on this condition, we can derive the speed of the train first. And once we have the speed of the train and we have a certain amount of time, then we can derive the distance, how many miles the train would travel. So the first step is to get the speed. Now, first of all, the distance can be expressed in many different ways. It can be expressed in miles, can be expressed in meters, can be expressed in kilometers. Same thing for the time. Time can be expressed in minutes, in seconds, or in hours, sometimes even in days, right? So you can see that there's many different ways to express the speed, and it will end up with different amount of numbers. So all it matters is the units you're using. So it means that you can use any unit that measures distance or time, but just making sure when you do the conversion, you need to use a consistent unit or the consistent conversion between those units. So again, we should always keep the units in the calculation to make sure that you are not using a wrong conversion rate. So first of all, the speed is distance over time. In this case, our distance is 1 mile. Time is 1 minute 3 seconds, that is 1.5 minutes. Okay, so now I'm using mile to represent distance, use minute to represent time. Here I have 1 over 1.5 mile per minute. That's my speed. I don't need to bother simplify this fraction yet because I need to do further calculations. I can leave the simplification till the end of the calculation. Now, second sentence or the question asks, if we know the time is 1 hour, what is the distance? Okay, so then the distance is now speed times multiplies time, right? Speed multiply time. Okay. Then speed is, we just derived that 1 over 1.5 mile over minute. And time, if I'm using 1 hour, hour cannot be cancelled out with minutes, right? But I know that 1 hour is 60 minutes. Right? Or in other words, can be written as over hour, right? But anyway, this case it's simple because 1 hour is 60 minutes, right? Now the minutes can be cancelled out, and it shows that eventually my results should only have the unit of mile, and unit of mile is the measurement of a distance, so it should be correct. So I have 60 over 1.5 mile or miles, and by calculating 60 over 1.5 give you 40 miles. So that's my results. So the train will travel 40 miles in 1 hour. Okay, next example. If you walk for 45 minutes at rate of 4 miles per hour, that's a measure of speed. Here it's short for the mile per hour. That's our speed. Then I run for 30 minutes at rate of 10 mile per hour, right? Because I'm running faster than I walk. So I have two different speed. One is when I'm walking for 45 minutes. The second speed is I'm running for 30 minutes. How many miles do I travel at the end? And what was the average speed or average rate? Okay, first of all, I have two segments, right? The first segment is the first 45 minutes with a rate, certain rate. Second segment is the last 30 minutes with a different rate. First of all, let's take the first question is how many miles do I travel at the end? So that's just adding up the two segments by the total distance, right? And we know that distance is speed multiplying time. Now our speed is given in terms of miles per hour. That means the better speed number one. we the better convert our time also into the unit of hours for this calculation, right? So my time one is 45 minutes. That is 45 minutes is equivalent to the conversion of 1 hour over 60 minutes, right? 1 over 60 is the conversion between hour and minutes. So then the minutes will cancel out. This gives 45 over 60 hour. And 45 over 60 is 0.75 hour. Okay, same thing. My second segment has a speed of 10 miles per hour. And the time 2 is 30 minutes. 30 minutes is just half hour, so it's 0.5 hour. Now I can take the total distance is my first distance plus the second distance. And my first distance is the speed in the first segment multiplying the time in the second in the first segment, and plus the speed and time in the second segment, right? So the first is speed is 4 miles per hour times 0.75 hours, then 10 per hour times 0.5 hour, and the hours can be cancelled out. All it left are miles. So this is just 3. So it's a 3 miles plus this is 5 miles. So totally that 8 miles. That's the total distance I travel. And then average speed, because I already know the total distance. So the average speed, because I have 2 different speed in 2 different time segments, but the average speed is to use your total distance divided by the total time you spent, right? That gives you the average speed. And I just know the total distance from the last question, which is 8 miles. And the total time I spent is 0.75 plus 0.5 hours, right? I just have the total time. Eventually, you will do the calculation, and finally, the division will give you 6.4 miles per hour. And that is your average speed. So that is 6.4 miles per hour. Okay, next question. Okay, this question, we have two friends, Ben and Alicia, lives 100 miles away. So in the morning, Ben departs at 7 a.m. with a speed of 15 miles per hour, travel to the east. And Alicia leaves at 8 a.m., travels to the west with a speed of 10 miles per hour. And then when or at what time Ben and Alicia would meet somewhere in the middle of their house, right? So first of all, I need to know the distance that Ben travels, and I need to know the distance that Alicia travels, and that they meet somewhere means the total distance Ben traveled plus the total distance Alicia travels should equal to 100 miles. That indicates that they meet in the middle. So how much time, and the question is at what time or when do they meet? So let's say we let t to be the time they meet. So by assigning this unknown variable t, we can use this unknown t first to express the distance Ben travels and the distance Alicia travels. And we know the condition that the total distance should equal to 100, then we'll have an equation that we can solve t from this equation. So Ben would travel how long? Because Ben departs at 7 a.m. So the time Ben spent, t minus 7 hours. For example, if t is 12 o'clock, then Ben spent 5 hours, right? If t is 10 o'clock, Ben spent 3 hours. So Ben spent t minus 7 hours in terms of time. And Ben's speed is 15. And Ben's distance of travel is then speed multiplying time, 15 multiplying t minus 7 mile per hour multiply hour. Okay, and similarly Alicia do the same thing. Now the difference is that Alicia departs at 8 o'clock, so her time is t minus 8 hours. Her speed is 10 miles per hour, right? So then the distance that Alicia travels is speed multiply time, this many miles. Now, to form the equation, the distance Ben travels plus the distance Alicia travels is 15 t minus 7 plus 10 t minus 8 equals the total distance of 100 miles away. Right, so then you can solve this equation. I will leave the details of solving the equation for you to practice. So eventually you can solve t from this equation. T will be 11.4. And t is the time, right? And usually when we express time, we say 11 o'clock, 12 o'clock, but we usually don't say 11.4 o'clock. So 0.4, we need to know how many minutes are there in 0.4 hour. So that's 0.4 hour times 60 minutes, 60 over 1 hour, so that's 24 minutes, right? Hours cancel out. 0.4 times 60 is 24 minutes. So this is 24 minutes. So the time is 11 o'clock and 24 minutes a.m. So that's how you solve this question. Okay, there's actually another way to solve it, and maybe faster than the first way. The second way is we can use a relative speed because they travel to the opposite direction, right? One is travel from east to west, the other one is travel from west to east. This is equivalent to say that one is stay still, stay steady, the other one travels with the composite of the two speed. So mathematically speaking, they are equivalent, or 0 and v1 plus v2. So then we can first move the time from 7 a.m. to 8 a.m. to eliminate the difference between the starting time. So Ben travels 1 hour earlier. So this 1 hour means 15 mile per hour times 1 hour is 15 miles. So Ben travels 15 miles between Alicia starts. So which means in order to convert the two velocities into one composite velocity, we taking out this extra 15 miles so that when both people start moving, their relative distance is 985 miles. If I set Ben to be steady with v equal to 0, then Alicia's speed is Ben's speed 15 plus her speed 10. That is 25. Sorry, this is 100 miles, so it's 85. It's 85 miles left in terms of the distance. So now I have distance, I have speed. So the time is distance miles over speed, which is 25 mile per hour. 85 over 25 is 3.4 hours. And we start at 8 o'clock. I remember we're eliminating the difference between the starting time. So this whole analysis starts at 8 a.m. So then the time they meet is 8 a.m. plus 3.4 hours. So that is 11.4 a.m. or hours. And we don't like this 0.4. Actually, you already see that we got the same results. So 0.4 hour is 24 minutes. So the time we meet is 11:24 a.m. So this is a different way to solve this type of question. Okay, lastly, we see some further examples with different rates. Like remember we said at the beginning that speed is a special case of the rate. Rate is something that measures a quantity change over time. So speed is the most typical measurement that we measure the distance travels over time. But there could be other rates also measures a change over time. So quantity change over fixed unit of time. So for example, if we have 5 wood chunks, chunk 50 cords of wood in 4 days, then how many cords could 7 wood chunks chunk in 6 days? Right, so number of woods or number of cords that chunked is also a rate. So first of all, we know that we have 5 wood chunks deal with 50 cords of woods in 4 days. So first of all, this means we have a ratio. If we fix the time, we have a ratio between wood chunks versus the cords of wood. So 5 wood chunks can chunk 50 cords. That means 1 wood chunk would chunk divided by 5, right? 10 cords in 4 days. And now we fix the wood chunk. We know that each wood chunk would chunk 10 cords in 4 days, which means in 1 day divided by 4. In 1 day, I would chunk 10 over 4 cords, right, in 1 day. Okay, I can keep the fraction for now because I'm not the end of the question. The question is asking you 7 wood chunk in 6 days. So now I will keep converting, or I can now convert the day to 6 days. So then still fix the number of wood chunks. Then multiplying 6 to the cords and the days, right, in 6 days. And then this is for 1 wood chunk. And then questions asking 7 wood chunks. That means I'm fixing the days and then need to multiply this by 7 times in 6 days. Right, so it's the number of cords of wood is then just 10 over 4 times 6 times 7 for so it's 105. So that's the number of cords that can be chunked by 7 wood chunks in 6 days. Okay, so this is an example of other rates, the rates other than speed. Let's see one last example of the rates. A water hose fills a swimming pool. At a rate of 0.5 gallons per second. Right? So this 0.5 gallon per second is the rate of a hose filling a swimming pool. If the pool capacity is 9,000 gallons. How many hours needed to fill or to fulfill the pool? Right, so then first of all, the speed or the rate is 0.5 gallons per second. And I have the distance or the volume is 9,000 gallons. So the time will be 9,000 gallons. See, if I'm using 9,000 gallons, multiplying this number, it won't cancel out the gallon unit and it won't cancel out the second unit, which means I need to divide by this rate. This is in order to cancel out the units and help me to determine how should I deal with the ratio or the conversion rate. Now it becomes second over gallon. Gallon will be cancelled out, and what's left eventually is the unit of time. That's what I need. 9,000 over 0.5 seconds. So that is 18,000 seconds. So I already have the time. I know that it spent 18,000 seconds to fill up the swimming pool. But the question is asking in terms of hours. So I need to further convert seconds to hours. So seconds need to convert to minutes, and minutes need to be converted to hours. So it's 1 minute over 60 seconds, and 1 hour in 60 minutes. In this way, second cancel out here, minutes cancel out here, you will have only hour left, and that is 18,000 over 60 times 60 hours. And you can do the math, and eventually they will be all canceled out to become 5 hours. Okay, so that's the last example of this lesson.